Hey there! Today, we are going to dive into the invisible world that's literally all around us, the world of gases. We're going to uncover these surprisingly simple, kind of elegant rules that control how they behave, and you'll see how they explain so many things you run into every single day. You know, it all starts with a simple question, just like this one. Why does a soda can make that hiss sound? Or why does a birthday balloon shrivel up if you leave it out in the cold? Well, the answers are all tied up in a powerful set of ideas called the gas laws. And trust me, by the time we're done here, you'll know exactly what's going on. All right, let's get right into it. Before we can start talking about the actual laws, we've got to understand the players in the game. What are the basic rules that all gases have to follow? Okay, everything, and I mean everything, starts with pressure. And it's not some weird abstract idea. It's the real physical result of trillions and trillions of tiny gas particles just constantly smacking into a surface. Think of it like a non-stop microscopic hailstorm. So the more impacts you get, or the harder those impacts are, the higher the pressure. Simple as that. So this right here, this is basically the physics engine that makes gases run. It's called the kinetic molecular theory. Now, here's what you really need to take away from it. 1, gas particles are always moving, bouncing around like crazy. 2, when they collide, they don't lose any energy. And 3, this is a big one. Temperature is really just a measurement of how fast, on average, they're moving. Now, those last 2 points about particles having no volume and no forces between them, that describes a theoretical, perfect gas, an ideal gas. And that's the simplified model we're going to use to build all of our laws. Okay, so with those ground rules set, we can finally start building our foundation. We're going to look at 4 laws, and each one describes a really simple relationship between 2 properties of a gas, like, say, pressure and volume, while we just pretend everything else stays constant for a minute. First up is Boyle's Law. And honestly, you already get this one even if you don't know the name. Just think about squeezing a balloon or using a bike pump. As you shrink the volume, the space the gas has to move around in, those little particles have less room, so they slam into the walls more often. And what happens? The pressure goes way up. It's a perfect seesaw relationship. You cut the volume in half, you double the pressure, every time. And we can even put some numbers on that. Let's say we have that bike pump. We take 2 liters of gas that's at 1.5 atmospheres of pressure, and we squish it down to just 1 liter. Well, the math backs up our intuition completely. The pressure doubles, hitting exactly 3.0 atmospheres. Next up, we've got Charles's law. This one connects volume and temperature. Look, when you heat a gas up, its particles get super energetic. They start zipping around way faster and push outwards on everything. It's why a hot air balloon rises, or why a bag of potato chips gets all puffy if you leave it in a warm car. If you keep the pressure the same, the volume has to get bigger. And this isn't just a vague relationship. It's a direct one-to-one thing. If you double the absolute temperature of, say, a 2-liter balloon, and, side note, we always use the Kelvin scale for this because it starts at absolute 0, which means no weird negative numbers to break the math. So you double the temp from 300K to 600K. And what happens? Its volume doubles right along with it, up to 4 liters. Okay, but what if the volume can't change? Well, that's where Gay-Lussac's law comes in. Imagine a totally sealed, rigid container, like an aerosol can or a pressure cooker. If you heat that thing up, the particles inside start moving way, way faster, but they have nowhere to go. So they just slam into the walls harder and more often. The result? The pressure just goes through the roof. And yep, the math works out just like with Charles's law. If you double the temperature in that fixed container, going from 300 to 600 Kelvin, you've just doubled the pressure, from 2 atmospheres all the way up to 4. Our last simple law is Avogadro's, and you'll love this one, because it's the easiest of all. All it says is that if you add more gas, you get more volume, as long as the pressure and temperature don't change. Seriously, every single time you blow air into a balloon, you're seeing Avogadro's law in action. You put more air particles in, they need more room. That's it. Okay, so we've got our 4 simple tools in the toolbox. But what happens when everything is changing all at once? Well, now we get to combine them into something incredibly powerful. This is where the magic really happens. So if we mathematically smush together the relationships from Boyle, Charles, and Gay-Lussac, we get this, the combined gas law. This is a major power-up for us. Now we can predict what's going to happen to a gas when its pressure, volume, and temperature are all changing at the same time. But wait, we can take this one massive step further. By bringing Avogadro's law into the mix, we arrive at the absolute pinnacle, the master key to understanding gases. It doesn't just compare a before and after state, it describes the state of a gas right now. And it does it with this beautifully simple equation, PV equals nRT. Let's break that down real quick. P is pressure, V is volume, T is temperature in Kelvin, of course, and N is the number of moles, which, don't let that term scare you, it's just a chemist's way of counting a really, really huge number of particles. Now, the secret sauce here is R, the ideal gas constant. It's the magic number that ties everything together perfectly. But here's the catch, and you have to remember this. Your units for pressure, volume, and temperature must match the units in R, or the whole elegant equation just completely falls apart. So up until now, we've been living in this perfect little world of ideal gases. But, the real world, it's a bit messier. So what happens when our simple assumptions don't quite hold up? Remember way back at the beginning when we talked about the kinetic molecular theory? We made a couple of assumptions. We said gas particles are basically tiny dots that take up no space, and that they don't interact with each other at all. Well, in reality, they do. They actually take up a little bit of space, and if you squish them really close together or get them really cold, they start to notice each other. They start to attract each other. And the real world also means dealing with mixtures of gases and how they move. Dalton's law is pretty much common sense, actually. It just says that in a mixture, like the air we're breathing right now, the total pressure is just what you get when you add up the individual pressures of each gas. Then there's Graham's law, which explains why a really light gas like helium leaks out of a balloon way faster than a heavier gas like nitrogen. Think about it. Lighter particles are the zippy sports cars of the gas world. They move faster, so they're going to find that tiny escape hole way before the big, clunky molecules do. So how do actual scientists deal with these real-world curveballs? Well, they upgrade their tools. Okay, I know, this equation looks like an absolute monster, but don't panic. It's really just our good friend the ideal gas law, but with a couple of little correction factors. That A part fixes the problem of particles attracting each other, and the B part accounts for the fact that they actually take up space. This is the pro-level version for when you need to be super accurate. Whew, okay, that was a lot, I know. We've covered a ton of ground here. We went from really simple relationships to a master equation, and we even took a peek at how messy the real world can be. So let's take a second and put all of these new superpowers into our toolkit. Seriously, if you're going to remember one thing from all this, make it this slide. This is your ultimate cheat sheet. From those basic one-on-one relationships to the incredible power of the ideal gas law, you now have a complete toolkit. With these equations, you have the power to predict and understand the behavior of the invisible matter that fills our tires, powers our engines, and even shapes our weather. So there we have it. We can now look at pretty much any gas and describe its state perfectly. We get its pressure, its volume, its temperature. We understand it. But, of course, that just opens up the next big question, right? Now that we understand how gases behave, what happens when we let different gases mix and actually chemically react? Well, that is a whole other story for another day.